Let us take a balanced star connected load. Okay, and the impedance in each phase, let it be Z angle theta. Now this point will be the neutral. So here you will have phase voltage VAN. This will be phase voltage VBN, and this will be VCN. Okay, and in a star connected configuration, the phase current will be equal to the line current. So here this will be IA, IB and IC. So this is the phase as well as the line current. Now VAN we can write as root 2 times the RMS value. So VP represents the RMS phase value into cos omega t. So if it is a ABC sequence, then you can write VBN is equal to root 2 VP cos omega t minus 120 degrees, and VCN is equal to root 2 VP cos omega t minus 240 degrees. Now since the impedance has an angle of theta, the currents you can write as IA is equal to root 2 times the RMS value we will take as IP. IP is the phase RMS into cos omega t minus theta minus the impedance angle. IB will be equal to root 2 IP cos omega t minus theta minus 120 degrees. So it is lagging A by 120 degrees. And IC will lag IB by 120 degrees. So root 2 IP cos omega t minus theta minus 240 degrees. Now the total instantaneous power of all the three phases we will get as the instantaneous power of phase A, which is the product of the instantaneous values of voltage and current, that is VAN into IA. Next is the instantaneous power of phase B, which is VBN into IB, plus instantaneous power of phase C, which is VCN into IC. So this will be equal to root 2 VP cos omega t into root 2 IP cos omega t minus theta. And for the B phase it will be 2 VP IP cos omega t minus 120 degrees and cos omega t minus theta minus 120 degrees. And for phase C it will be 2 VP IP cos omega t minus 240 degrees into cos omega t minus theta minus 240 degrees. So here we will make use of the trigonometric relation cos A cos B is equal to 1 by 2 times cos A plus B plus cos A minus B. So now P of t, the instantaneous value of power, this will be equal to 2 VP IP you can take as common, cos omega t into cos omega t minus theta you can write as 1 by 2 into cos A plus B, which is cos 2 omega t minus theta, plus cos of minus theta, which is nothing but theta, and again plus 1 by 2 cos 2 omega t minus theta minus 240 degrees plus cos of minus theta is theta. Again plus 1 by 2 cos omega t minus 240 you can write as cos omega t plus 120. So you will get cos 2 omega t minus theta plus twice of 120 will be 240. And again you will have cos theta. Now here we will use one more trigonometric expression, that is cos of A minus B is equal to cos A cos B plus sin A sin B. And also cos A plus B will be equal to cos A cos B minus sin A sin B. So now you can write the instantaneous power as 1 by 2 you can take out common. So you will get VPIP. Cos theta is appearing 3 times. So you will write 3 cos theta plus cos 2 omega t minus theta you will leave as it is. And this cos 2 omega t minus theta minus 240 you will use this expression. Okay. So this is where you will get cos 2 omega t minus theta into cos 240 plus sin 2 omega t minus theta into sin 240. And similarly, cos 2 omega t minus theta plus 240, here you will use this expression. So this you will get as cos 2 omega t minus theta into cos 240 minus sin 2 omega t minus theta into sin 240. Now here this expression and this expression will cancel out and this is appearing twice. Okay. So this will be equal to VPIP 3 cos theta plus cos 2 omega t minus theta plus 2 cos 2 omega t minus theta into cos 240. So now here cos 240 is minus 1 by 2. So this you will get as VPIP 3 cos theta plus cos 2 omega t minus theta, and this will be 2 into minus 1 by 2 will be minus 1. So minus cos 2 omega t minus theta. So you're getting the final expression as 3 VPIP into cos theta. So VP and IP are the RMS phase values. So you're getting the instantaneous power as this value. So you can see that it is not a pulsating quantity but it is a constant value. Even though we have derived this for a star connected load, the same will hold true for a delta connected load, and you can do the same type of calculation to verify that.